Welcome to another coding session. Back with Bangalang. We've just managed to add in arrays and the ability to copy arrays around. So we can see now that we can pass an array as a parameter in here, and we also return an array. We did do just like a straight copy up here, but I guess we got rid of that. So we're doing pretty well with arrays. But it would be nice if we didn't have to actually copy it in, which is why I'm pretty excited to have a go at pointers now. I don't think we'll do the array parameters straight away. I think we're just going to do something like equals, this is going to be the symbol I'm going to use for pointers. So this is going to be a pointer to something. In most languages they use the ampersand, but I noticed in Odin they use, and I think maybe some other newer languages, they use this as the pointer when you're doing a type. So I kind of think like, if you say that's the type which is a pointer to something, why don't you say that that's also used here? So anyway, that's what I'm going to use for pointers. And the other thing you might notice here is that you don't need to do something like this because it's auto dereferenced. I think the other way that you would be able to auto dereference is if you had something like that. We don't have structs yet, but if you had a struct and this was a pointer, you would still be able to use the dot notation. That's my intention. Anyway, so I think this is the first, we'll just do step by step. I think the first thing is we'll just try to do this. This is already quite a lot actually. The ability to create to create a pointer of something, and then to index into that, which is going to implicitly, I mean, most things in this language are explicit, but here we're going to implicitly dereference. So you can think of this as dereference and then index. But first, before we start into that, I found a bug. I remember at the end of the last video, we were working on this return because we changed our calling conventions so that we return to the stack. And we had errors here and we managed to fix them. But I remember at one point there was like 2 identical copies here. And we still have this copy, which is pointless because we're copying from there to there. Like it's just copying to itself. And I realized why. It's because in here I had intended to do this. And because I didn't, it was going into here, but then because there was not an else there, it was like also going into here and eventually doing this. But actually, I think I would rather do something like this. I like to have guard clauses, early outs, whatever you want to call them. So if they're the same, then just return. There's no need to continue in this procedure. So if we compile that, we need to take, we have comments now. I could comment it out. That's nice. Yeah, so now that extra redundant copy is just disappeared, so that's nice. Okay. So if we go back to our source code, we put that back in. How are we going to implement this? Well, first, we need to look at our grammar. And I realized that actually the way that I'd done it before, this variable production, which is used within the primary production, which is part of an expression, it meant that you could put this index at the end of a variable. But I noticed that in the last video, what I instinctively did was try to do something like this. And it was not possible because we only said that you could put this on the end of a variable, but this is not a variable, this is a procedure call. And I think the solution is we're going to keep this variable thing here because we need it for assignment still, but we're not going to use it in the primary anymore. Instead, we're going to just call that an identifier. And I actually want to take this negation and put it right at the front here if I can figure out where that is. It can be quite hard to understand what the hell's going on here with this syntax. So we have this negate primary at the front here now. And I want to expand on this so that you can put a hat. So that's the that's how we reference. And then I also want to have a primary that can have this index notation after it. So what we're saying is we'll put a little group here. And then we'll put another text there, and I think I'll put the hat first. So now we can say we put a hat or a minus before a primary. And then after the primary, we should be able to put what was it? This bracket thing here. I guess it doesn't need to be in brackets, does it? Is it like this? Yeah, so you can have a primary prefixed with these or a primary suffixed with this. Okay, those things are valid in this primary here. This variable here is just, we're just going to leave it like that. We're not going to add any pointer stuff to this yet. I just want to, do a little bit at a time. Oh, there was something up here I'd noticed that in statement I forgot to put 4. So let's there. 4/. Yeah, that's been bugging me for a little while. That wasn't there. Okay, so now how do we implement this? Well, we have a single new token, which is the hat. I call it the hat. I don't know if that's a technical term, but it's good enough. So that's it for tokenization. We just need to be able to get a hat token. Parsing, we're going to change a fair bit. So I think this is actually potentially a switch, isn't it? Partial switch. And I like to use switches where they make sense. So I'm going to do that. Let's put this inside the switch. So we go case that guy and case that guy. It's like that. And then case minus goes like that. What's going on? Our indenting is all messed up. Yeah. Once we get this, soon the indenting should fix itself. Oopsie. Like that. And then this last one must be the default case. There. Okay. So now we converted it to a switch. I do like to have everything in the order that it is in the grammar. So our minus is going to go up the front here. But the hat will go before it. And then we also need to add like an index potentially we have an index in here. So I guess this is going to be pretty much the same. If we come across a hat, we consume it and we say, I'm going to say it's a reference node because we're creating a reference. Minus, and we need to be able to, all of these things come before the primary. But if we want something to go after the primary, we kind of have to parse it. So I think we need to, like, after the switch, I'm going to make it another switch, even though there's only one thing, because I think we're going to pretty quickly add more things. So we're going to peek what came after the primary, essentially. Yeah. I'm going to peek what happened after the primary. I think this way to do it makes sense. And if we found, what is it, an opening square bracket? Then we want to do the stuff which I think is in parse variable, right? Yeah, this is where we did it before. So it's kind of like this. Business. What does this do actually? Consumes the opening bracket, then sets the data index to the next one, and then consumes the closing bracket. I think that sounds right to me. I think that's all it needs to do. This did parse identify, but we've already done that, so that's not needed. The parse primary would have taken care of that. Oh, do we need to put a node type in here though? Oh yeah, because we're this. So this is not right, because we're. Oh no, because we're just appending a data index. Is that right? No, I think what I want to do. Is I want to add an extra node. You know, like we do with negate. Negate is its own node. Reference is its own node. And I want to make like another index node. So we'll save the node we already have, which would be the result of, whatever it is that, lots of things will assign nodes, or it could be a reference node, even a negate node. Whatever it is, we're going to save it to the side, and then we're going to create a new node. I think we're just going to do something like this, and we're going to use named parameters. And that way we can supply whatever parameters we want. I'll call it index. What else do we need to put in here? Well, I guess the data index. And the metadata. Which I guess we can grab from the child node. Column number. Yeah, so then we create this new node and we add the child node to its children. Like so. Yeah. So we need to add these new types. That's a reference and index. And that should make this happy. So I think that's the primary sorted. Was that the only thing we changed? If I go to the source code view, the only other thing we changed was this, but that was just fixing an error. So now we handled both of these prefixes and the suffix, I believe. And we have we have identifier here. So this is not parse variable. This is just parse identifier. All right. Okay. Yeah, and because no, let me have a look in here again. I just want to have an extra look. So we can reference the return of a call. We can reference or index the return of a call. We can reference or index an identifier. I mean, referencing the return of a call could be dangerous. I don't know if we should allow that, actually. You definitely can't reference or index a number. I think indexing a number, actually, the way that I've coded it so far would not be a problem. You would just have to index with 0. Or if you had a higher number, it would just say out of bounds. But you definitely can't reference a number. You can only reference a memory address, I think. So I'm just trying to think about that. That's kind of type checking stuff. But I think we've got all of this converted to the new way of doing things. Let's see. Now when we go to type checking, we need to change the way we type check primaries. Yeah, so we'll move this negate up here. And before negate, we have the reference. And after it, we have the index. One thing I had thought about before, and I think this is the case, like we do type check primary, which will fill out the data type of this first child node, but we never set the data type actually of this node. And a negation does not change the data type. So I think what we actually want to do is that, just to make sure, data type, just to make sure that the current node does have the correct data information. Because then when we filter up, like this could eventually filter up to here. There's a type checking of one of these sides, and then we do a coerce types. And we find out that this type information is just empty. So I think we need to make sure that's correct. And then we should probably actually do our checks based on the current node. So you can't negate an array. Makes sense. And now that we have pointers, you can't negate a pointer either. Although we don't have anything that says you are a pointer. It's a bit confusing, I know, because I'm sort of interchanging different terminology, but for the purposes of what I'm doing, we'll just call a reference and a pointer as just this. It's the same thing. That's caused some errors. Yeah, we can't declare a type as a pointer yet. We'll need to update this later. And when we pass an identifier, at that point, it is not a reference. So when we parse, I think that is something that I have missed out actually. When we do this, when we index into something, we parse an expression. Yeah, we haven't really, there's not really type information right now. So I think, because I was thinking like, oh, should we set up some type information now? Like we know the length is 1 now, but yeah, that's right. I think the way that I have been thinking about this is that parsing is just taking the information that you can see directly in the text and putting it into the AST. It doesn't infer anything. So all it knows, like with the hat, it just says, okay, there's a reference going on here. And when we have this opening closing bracket, yeah, because this is the primary, yeah. I was actually thinking about this opening closing bracket. And we do set the data index here because it's part of the text. Okay. Yeah, all right. Anyway, got a bit sidetracked there. So yeah, when we negate, we need to make sure that it's not a reference. Oh, no, if it is a reference or an array, then and put that first. Then it's not valid to be negated. If we go up to reference, I think when we reference, we also need to take the data type from the child. In this case, we want to say that the child cannot be a reference itself. Yeah, we don't take references of references. Not yet, just to simplify things. But we can take references of arrays, that's fine. So we just go like that, and then we say is reference true. I'll put it up there, it doesn't matter. We just need to make sure that the child was not a reference. And then when we index, we need to make sure, well, a length of 1 is fine. So indexing we kind of took care of down here in variable. First we made sure that that was existed. But I think that can be, because now this is identifier. And, oh, there is no type check identifier. I think this is the type check identifier. We just need to make sure the identifier exists. That's type checking an identifier. I kind of don't like how we're like duplicating this stuff, but yeah, we'll fix that a bit later maybe. I have a feeling that we'll eventually merge some stuff together. So here's our indexing. So we type check the child, and then we do something like this. Probably not quite like this. So we know that the data index is not -1, because if it -1 means that you didn't index into something. But if we come across an index node, we know that we indexed into something. Yeah, we were looking at it just before, so we set the data index to a proper value. So that never happens. So we know that it's this case. We know the variable exists. So actually this part here is probably do that here, right? variable data types. Yeah, we know the variable exists, so we get it, and we get its data type. It's okay to do this before this condition, because in Odin this will just return an empty object, and that's totally fine. I mean, it doesn't matter if this is dodgy because we're going to fail the type checking anyway. Failed to type check variable, that should be primary now because we're in the primary stuff. So we don't need to do this actually, we just need to set the length to 1. That's what indexing does to the type. And then I guess we need to check against this, right? If the child's the length of the, if the data index, what's this okay and? If okay and. Oh, I think that was to prevent, because we were getting like double errors. And I found it kind of annoying. Let's just get rid of that. So yeah, here we put the length to 1, but then we check the child's length, which should not be null, 1, or it should be, it could be longer for a longer array. And we make sure that the data index of this node is not out of bounds. Okay. Node.value. I feel like this is going to have to be the child value actually. That's what it's out of bounds of. This one's just similar type. So I think that's the primary sorted. I guess this is false. This is complaining because I haven't told it whether it's a reference or not. Probably the same up here. Yeah, those tests. Okay. So I think we're type checking our primary pretty well. Is there anything else that we really changed? No. I think that's it for type checking for now. And generation, I think, is going to be the tricky part. So when we're in our primary, let's chuck our negate up here, and up above that we have our reference. So how do you create a reference of something? I think we're going to have to do some. I think this is all pretty much. This is almost right. So to create a reference of something, I think it's kind of like we did before in copy here. So source and dest, in this case, we know they are memory locations. And to get the address of those memory locations, we used load effective address into a register. And that's exactly what we're going to do here. So if it's a reference, this must be a memory location. So I don't feel like we have our type checking working so well, because this is kind of saying we could take, I think at the moment we could take a reference of a number. This is kind of like what I was saying before. Take a reference of this or of this, which I'm not so sure about. Is there something quick? I mean, I feel like it's not super urgent, but I wonder if there's something quick we can put in here to prevent that from happening. So if we do a reference invalid type, so the child can't be a reference. And also the type of the child. Yeah, I guess the tricky thing is that it could be. No, I think it's going to be a little bit complicated, so I'm just going to leave it for now. It's a bit dodgy, but I feel like it's not the most important thing right now. More important is I want to show you how to do this. So to reference, we're going to load the effective address of something into something. So the register is where we're going to put it, and the primary destination. Don't know about this naming convention, but so the primary destination, this should be a memory address. If it's not a memory address, we're going to get assembling errors, which we don't want. We'd like to stop that in the compiler. But so this is the address which will show up here. This is the register it's going into, and it's saying put that address there. That's how you reference. I think it's just that. To index something, we should have already code that does that, right? Where do we index right now? I feel like it should be in the variable. Oh, here it is. So when we're taking care of an identifier, this part here is the offset, the index offset. See, this is the data index times the size of the element in the array. So now that we've wrapped this identifier node with this index node, I think we take this and put it up here. This is to be used up here, not the variable position. So the variable position goes here. So the result of the identifier node is that we get the memory address of the identifier, right? And then the index should basically offset that memory. I think that's all it needs to do. So I think that would be quite simple, right? That when you just take this offset, and this is the destination that's been sent in, so that's this. No, that's not that. That's the primary dest. That's the primary dest. So you just go primary dest.offset, and you add this. So that's kind of the equivalent of what we did. This line used to be in here, and we just moved it up here. Do we need to move to a register? I don't think so. I think we can just return that. Now, we said before, this is what makes it tricky, that if we do this, so if we go, maybe it's easier to see here. So here, we're indexing. So in this case, we have an index node that wraps the identifier node. But because this is a reference, see, it's been assigned to as a reference, we need to dereference before we do this index. So there's kind of like an extra step in the middle. If the what am I checking? If we're a reference, So does the index node have that information? Let me just see. So index, that is something I think see here we like assign the data type. Here we assign the data type. So I think we need to do that here as well. So we take on the data type of the child, but we override the length as 1. So that means that this data type reference should contain the correct information. So we've said that this case is when we don't. Let me just put this in here. I think this is probably wrong, but move to register. Let's put that up here too. Well, here, no. I think all we need to do here is add an offset to the primary destination. So this register thing does go in here. So how do we do this? How do we take a reference? Or how do we dereference? This was taking the reference, and now we need to do the opposite. So I asked Grok about this, and basically what he said was something like this. So if RDI has a pointer in it, you just move that into another register, and then you again use that as a memory address by putting square brackets around it. So we want to move to a register this primary destination. We'll move the primary destination to a register. Yeah, because what's held inside this primary destination is the reference. So now we have a register with the reference in it, or with the memory address in it. And then we need to and that's also going to be the size we know is going to be 8, because we're moving it into, because this is a pointer, right? Pointers are always 8 bytes, 64-bit. Is that also the case here? Effective address. Yeah, so this register also needs to be 8. So we put it into an 8-bit register. So this, now we have the address of what we want here. And then I think, can we just return that as memory? Register dest. And this is where we use, we need to have the offset also. So we'll put the offset here like that. Yeah, so here we just add it to what we already had, but here we put it here. Is that really it? So this is a register containing the address. So then we just use that register as memory itself. We'll create a memory location of that register. I think once we see it in assembly, it'll make a bit more sense. And I think something that might help. So we've got move to register. I kind of want to, okay, so we won't do it yet, but I kind of want to, because this is just going to say move to register. Well, actually, it's just going to say copy. And I want to have some comments that are a bit better. But is that all we need to do? We just need to change the primary like that? That might be it. Let's see what happens if I try to run that. So we get exit code 0. I do always like that. And this is what we're really interested in, this part here. So after the loop, there's declare, assign, declare. Here's the loop. So declare, assign, declare. This is what we're interested in. So we're allocating 32 bytes on the stack. That already looks wrong to me. We're copying the address of the previous array into a register. And then we're loading the effective address of that same thing. And then we're moving that. So this here looks right. We take a reference of the other array and we move it to here, to the thing. But this should not exist. And this should only allocate 8 bytes. So let's tackle the allocation first, because I think I know what that is. Let's find an example of this. Here we go. So this is the kind of thing where we're deciding what size something is, and we multiply it by the length. And when we have a reference to something, we still include the length of the thing that it's referring to. And also the data size is still the thing that it's referring to. So in this case, it's 8 times 32 bits, which is 32 bytes, which is why we have 32 here. So I think what I want to do is maybe create a little utility function. Which returns an int. And then we say, oh, and we need to pass in a data type and the context. And if the data type is a reference, we return 8. We just override the size as 8. So now I'm just going to look for this string. Oh, it's not that string. Where was that example again? Like this. So anywhere that looks like this, we're just going to say byte size of data type context, like that. Oh, but what data type was it again? No data type. So this one is param node. What else we got here? This one I think we can just put straight in here. Another, I did kind of think that maybe we'll change this to byte size. I don't know. To go along with this here. So this one does not even get used. Huh, that one's pointless. Does this one get used? Yes. Okay, gets used twice. So let's go like that, and it was the left-hand side node that was used. And then we have some up here. So this is when we're allocating space for a procedure call. So that's param node. Yep. I guess this time it's just like that. Yeah. And this one is just node. And there's an error down here because that's return byte size. Yeah, so every time we try to find the size of something, we just say that it's 8 bytes if it's a reference, because references are 8 bytes. Yeah, so now we're allocating 8 bytes. We still have this stupid copy here. I kind of want to know what that is. I don't think it's like a super big issue, but it's just pointless. Yeah, we do a copy and then a reference. Okay. So where do we do a reference? I think that's the only place where it actually says reference as a comment. Oh, so we do a move to register. Yeah, that's pointless. But we do need an 8-byte register, and if we just use, we don't know if dest is an 8-byte register. We need an 8-byte register in this case. So instead of move to register, I'm just going to say, hey, I want an 8-byte register. Yeah, I think that's that. There we go, that looks good. So we allocate some space, we get a reference to RSP plus 8, which is the previously declared thing, which is the array. And then we put that address at the top of the stack. Perfect. And then when we return, yeah, so this is interesting. So when we return, this is the auto dereference. So yeah, this is where I would like to change this so it says dereference. But yeah, it's taking whatever's at RSP and putting it in R8. So now R8 is the address, and that's why we do, like it's the address of the array, and we go address of the array plus 12. Each element is 4 bytes, so that should be the third index. Yeah, third index. And we put it into the return code. And we get 4. That's perfect. Okay. Awesome, awesome, awesome. Wow, super happy with that. Yeah, that's it. Okay. So now let's try something a little bit more difficult. Let's say that, oh, I'm surprised that that wasn't an issue. Remember, that was something we mentioned. I don't want to tempt fate, so let's not have that there. Ah, but we did fix it, didn't we? We did fix it. No, I'll leave it off for now. I feel like it's so dangerous to try and test too many things at once. So I just want to say that I don't want to copy the whole array in. I just want to send a pointer in and do the increment. And this returning a copy is pointless, but we're going to do that still anyway. Yeah, so I just want to pass that in. So now we need to have the type needs to be able to be a pointer type. So this is our type down the bottom here. So I think we want to be able to prefix it, optionally prefix it with this hat. So here's the hat. here's type. That's it, right? Yeah, I think that's it. So we just put question mark there. Is that it? Oops, that's the wrong place. Yeah, so hat token, which is an optional data type, and then optionally you have the index afterwards. So anywhere you put a type, you can do that. So when we go into parsing, there should be a parse type in here. There we go. Currently we're saying it's not a reference, but that might not be true. So if we peek the first token and find a hat, well, I'm afraid that means that the data type is a reference, like so. And we need to consume that hat. Okay. So we don't want to override with false here, so we need to split this stuff out. So this is kind of the length stuff here. So maybe here I'll initialize the length to 1. And here we're just talking about the name. Like that. So now we should be recording our type information, which optionally includes that it's a reference. So we can say that's a reference, and then this also has the reference type, so the type checking should check out. Yeah, I don't think we need to add to type checking. It works. Well, we do need to, where is it, our coerce type? Coerce type. We probably should have done this before, actually. We need to make sure that they're either both references or they're not both not references. Otherwise, they are not compatible. So that should still pass, but if I take that off, it should fail. But it calls them both the same thing, because the other thing we need to do is this data type name. We need to put the hat on the name so that we can tell the difference. So if length is greater than 1, we do this, but instead of returning, we say name equals name with brackets on the end. And if it is a reference, and down here we just return name. And if it is a reference, then we put a hat at the start, like so. Yeah, and then we get incompatible types because one's a pointer and one's not. But if we go like that, then everything's gravy. So type checking is all good. Generation, I'm really not sure about. I mean, so we've done expressions. So I feel like that should handle the. I feel like the call should be okay, because we're using the right sizes, and we're just doing an expression. And also the return. I feel like they should be okay, but what about when we declare the... Well, that's only about sizes, isn't it? That's all it is. Let's see what happens. We get exit code 0, so this is, yeah, here we go. This is the function call here, the procedure call. So we allocate 32 bytes on the stack. That's for this guy, which is a full array, so that makes sense. Then we allocate 8 bytes because that's the pointer. We take a reference of something up here. Hopefully 40 is correct. And we copy that to the top of the stack. That sounds good. And then we allocate another 32 bytes, which is our temporary space for our return. I mean, in this case, it's kind of redundant because now we're just going to do this. We'll do this copy down here, which takes it from here to here. So we could definitely optimize that. We're just doing a redundant copy. But if this wasn't a declaration, like if this was this here was a pre-existing variable, which already had space allocated, well then also we could just, okay, yeah, I feel like that's definitely an optimization we could do at some point. But yeah, so that's this temporary space. Then we do the call, then we clear and copy back. This is all normal stuff. This is pretty much the only thing that's new. Now if we go down here, we copy RSP plus 40 into R10. And we get R10 plus 12 and put it into, yeah, so this is our, so increment, so what is the line here? So these are going to do a dereference, both of these. I would really like to see dereference as the label. Let's see if we can't do that, because I think that's going to make it a bit easier to understand what's going on. So this move to register, no, this move to register here is a dereference. I think I might rename that to copy to register. And I want to be able to go like this, dereference. Yeah, so that'd be like a comment string, and I'll give it a default value of empty string, which we just pass on to the copy. And we'll say comment equals copy and no, a final comment. And if comment is not the empty string, then final comment equals comment. So it overrides it. And then all of these are going to take the final comment as a parameter, and that becomes a %s. I don't think I want the do it anymore. I was kind of becoming less of a fan of the do it, I must admit. Do we have any more do its? This one can just be divide. Yeah, let's try that. Yeah, okay. So now we can see it's a dereference. And then, so then we use that address, an offset of that address, because we want 3, so 12 is correct. And then we increment it, and then we should be putting it back. But this is not getting dereferenced. This is doing some weird shit. So what is this? It's an assignment. So this copy here would be the actual assignment part. So this here is the variable on the left of the assignment. So declaration assignment. Okay. So on assignment, because this variable also has this array stuff, we need to be able to detect if it's a reference and auto dereference if that's the case. So if LHS node.datatype.isReference, is reference, Then how do we do this? Okay, I think like the other time, we need to sort of separate out the offset. We can look at what we did in here. Let's bring this up. It's kind of like a cheat sheet, you know, except we need to talk about the left-hand side node. And instead of returning it, we're actually doing a generating expression with it. We have to actually declare that. So here, I guess we're using the primary dest plus offset. Is it just that? Yeah, if it's not, yeah, we just do what we did before, right? We just do what we did before. I mean, if there's no dereferencing to happen, then it's all good. Yeah, because this is the indexing part here. Now we need to copy to a register. Register 8. Do we need to copy to a register? Yeah, I think so. And what do we need to copy there? I think we need to take the variable position. Yeah, so this is where our pointer, our reference is. And we're going to copy it to, I mean, we don't really need, I think in this case, it's probably a bit clearer to just just create a register, right? We just want the 8.8 register and then just do a copy. Is that it, or am I missing something? Source, destination, size, comment. File, source, destination, size, comment. Oh, it doesn't assign. Right. So we get a register. In this case, we're going to do R8. But this expression might mess with R8. So what's a register we're definitely not going to have used? We could use, the expression could use numbered registers, and also here it uses AX and DX. I can't remember what all the different register names are. I thought maybe this register named might do it. Okay, so let's just, I mean, we'll just use RBX at the moment because I feel like that one's not going to conflict. Where were we? Assignment. So we use BX. I mean, I don't know if this is a good idea, but that's what we're doing. If we run that, we have another look here. Yeah, so here's two dereferences. And because we're assigning it to itself, they should be identical, and they are, and that's great. And this here looks like an increment to me, right? Like we copy it into a register, we add one, and then we copy it back. We just have two different kind of pointers going on. Nice. Okay. I think that's what I expect. And then the return is copying 8 bytes back. Really? It's only copying 8 bytes back in the return. I feel like that's not quite right. If we go back into, no, I'm getting a bit lost now, but this here, it's returning the whole array. So it should be a 32 byte return, right? And it's only got an 8 byte return. So that's the generate return, I guess. Do we need to do anything funky here? Wait a minute. That's correct that it copies 8 bytes because this is a pointer that it's copying back. But we want it to be an array. So this should fail type checking. Should fail type checking. Yeah, that expression should fail. Does it not fail? Index. Well, it's definitely not an index node. It should be just an identifier node. That's a call. There's an identifier. The value is array. Yeah, that's it. Okay. And the data type of that is a reference. We've got expression okay. So it passed the expression even though this is a reference. This is a reference and this is not. So they should, I did put that in type coercion, so that should fail. So what's it comparing against? The procedure return type. That procedure looks totally empty. So yeah, we go through and we create all the procedures. We add the return data type comes from the node data type. So that looks right. When we type check a procedure, we set the current procedure that we're in before we type check the scope. Yeah, so we've done that. Then we go into the scope, into the statement, into the return, but it's empty. But we set it up here. We copied it and set it. Oh. I noticed two things. The first, it seems like I felt like that was required. And then second, I don't even copy the individual procedure at all. Okay, now we seem to have the right type information. So that's correct, right? We can't do this unless this is a pointer also. And then it makes total sense that we cop 8 bytes back. And then here, this thing. Yeah, so now we're saying that what we assign to is also, like this is also becomes a pointer and it should auto dereference. I'm confident from there, oops. 5, last time it was 4. Oh, no, because we're doing increments, so that's why it's gone to 5. Nice, okay. I think that's working. Where are we at? 110. Okay, let's try it. we're already at 110, but I want to do this. This is the other way that we could do it. We can return a full array by dereferencing here. So yeah, this on the left is reference, this on the right is dereference. So the result of this should be like this is the pointer to an array, and this is the array itself. Let's try that. Let's see if we can quickly smash that out. So that is, you can't declare a type that has that, but the primary can. So it's got like this indexing, and I want to have the hat be on the right-hand side as well. Where is that indexing? That's it there. So put that in brackets. It's so hard to read this stuff. And we put the hat here. Yes, primary followed by a hat or index. And because this is recursive, it could have both, you know, and it should still work. I don't know if I want to test that, because if it fails, it means I have to do something about it. Parse type, we don't need to worry about that. It is parse here, opening square bracket, but it's going to be something, I guess, similar to this hat business. So if we find a hat, I guess we do need to kind of follow this pattern. And, well, it's a dereference node. We don't set a data index. I think that's it. We just say this is a dereference node. Like that. So we have reference and dereference. I think that's all I changed, right? So now we go to type checking. Type check primary, and we have negate index. Before index, we have dereference. So we do the primary, then we go here and we say it's not a reference anymore. If the child wasn't a reference to begin with, like you can only dereference a reference. And notice we just have true or false here, like, and I disallow up here, I disallow explicitly, like if it's, you can't reference a reference, which is something that ultimately we should be able to do, you know, you should be able to go like that, and then you get a pointer to an array. That should be valid, but right now we're not going to support it. I don't know, I can't remember if I mentioned that before, but here we saw a dereference, so we just change the reference back to false, basically. Yeah, and that's the only restriction, I think. We had to have been dealing with a reference to begin with. So I think that's that. And then when we, where's our, this looks like call. Okay. So we have reference, negate, dereference. So dereference is what we kind of have in here, right? So we don't have this offset because this is the indexing part. But we generate a primary. And then do we just do that? with an offset of 0, I guess. We dereference, so we like take this should be, if we have a reference to start with, this should be an address. We do this dereference, which takes this address and puts it into a register, and then we treat that register like memory. So this line here is what I'd be quite curious about. And we should end up like, this should be an array in the end. Yeah, so see, we've allocated a full array as our, what we're assigning to. So this is a full array. We're passing in a pointer, and this is our temporary return place in our copy, our redundant crap. But inside here is what I'm curious about. So this is what we had before, but our return, we dereference, right? We dereference, which should give us an array. And then we copy from that address to +8. Is +8 the correct location? Yeah, because we don't declare anything in here. So this 8 is getting past the instruction pointer for the call. Yeah, and we copy 32 bytes. We copy a whole array. I think that should work. Five. Wicked. So we have referencing, dereferencing. I reckon this should work too. It compiles. Damn. I thought that might work. I thought that might work. So what did we break with that? So when we parse, we have just a primary, which is a call. So this is a nested expression. So it's just a call, should be a call node. So when we come into parse primary, we go, it was an identifier, we figured out it was a call. Great, so this is a call node now. And then we come through and we go, what was after the call? Well, we found some square brackets. So we put that there, then we say, hey, here's our index node, and we do that. And type chicken's fine. And then when we go into here, we come in and we're like, hey, we found an index node. So let's do this thing with the child where we get the primary destination. So yeah, we're getting the child and we're saying, hey, this is the offset to index 2. And it's not a reference, right? What we return? Yeah, we're returning a full array. So it's a full array. I wonder if it's because, like, what is this address actually? That's where the result of this goes. So that's actually the result of a call, which gets put into dest. Okay, so it's in like the final destination. And then we take what's in the final destination, we dereference it. Oh no, we're not doing a dereference. So we just offset from it, and then we say, hey, that's our destination now. I feel like that makes sense, you know? So let's see what it actually says. Within the function, I expect nothing should have changed in there. But when we return, this is the copy we do. So we say RSP minus 40, and we copy it. But that should be that's the first element. I know, because that's how much so that should be that's the first element, not the fourth. So I feel like it's not using the data index. And the index node is the one that should have the data index, right? The index node has the data index. Can I just debug here? Sorry, we're going a bit over, but I'd like to I feel like this will round it out nicely, you know, if we get this sorted. So we're generating a primary. Jesus. Okay, I'm not sure what the deal is with that. But the primary destination is garbage. Well, that could be an issue. That could be an issue. What is the destination? Yeah, it's RSP plus 12. That makes sense to me. But what we get back is garbage. So dest is garbage. So there is a dest, so we should have moved some stuff into it. That shouldn't have changed it. So it's kind of like maybe the return has put some garbage in there, but I mean, returns have worked so far, right? Oh, this is type checking. Declaration assignment. So this is the return. I don't think the return needs to do anything special. I don't know why that's garbage. And you know what? I'm gonna leave that for now. Maybe I'll make it a known issue. I've got some notes over here. Known issue. Known issues. Cannot index result of call. Yeah, we'll just make a note of it. All right, but I mean, even though that's janky, I mean, I'm sure there's a ton of bugs in here I don't know about yet. I'm pretty stoked with all that kind of pointer stuff that we've managed to do. We have referencing, dereferencing, auto-dereferencing when it comes to indexing. I think that's awesome. We can even, like, you know, pass pointers in, return pointers. We did both of those. So that's wicked. And speaking of bugs, of which I'm sure there are many, I think I'm going to sort of build towards in the next couple of episodes have the ability to have asserts and print messages when something goes wrong, and then we can create some tests, like a file just full of testing all sorts of different things, so we can run that and sort of verify that everything's working correctly. And just like think up lots of different cases to test. I think that would be, yeah, I think that's starting to get more and more necessary now that we add more and more features, and when we change something, we could break something else quite easily. And yeah, I think that's going to get more important. But we've gone very long, so that's enough for today. Thanks for stopping by. Yeah, have a good one. Ciao for now.